Hi everybody, in today's video I'm going to be going through the notes for Unit 1 Lesson 2, which is an introduction to limits and graphical limits. Here are our learning targets for this lesson. I can write a limit statement using correct notation that references a given function. I can estimate a one-sided or two-sided limit given the graph of a function, and I can justify why a limit does not exist at a point using limit statements when necessary. Now, there are a couple key words in these learning targets that I want to point out to you. One of the things you're going to notice, and we use this phrase a lot in calculus, is that we are going to be using correct notation. How you communicate your ideas mathematically matters, and specifically in calculus, the way that we write things and changing the way you write things can communicate things differently. So when I say using correct notation, that means it's how you write it correctly. And it's really important that you do this because it communicates your mathematical thinking. The second learning target here, and this is something really important, is that we're going to be estimating today both one-sided and two-sided limits using a given graph. So there are lots of different ways we're going to estimate limits. We're going to estimate limits from graphs. We're going to estimate limits using tables. We're going to estimate limits using functions and equations. Today, we're going to start with just what is a limit, how do you write it, and how can you use a graph to find it. Finally, I can justify why a limit does not exist at a point using limit statements. This idea of justify in math means explaining why your thinking is what it is. Now, justifying in math does not mean we're going to be writing paragraphs necessarily, but it does mean we're going to need to give an explanation in a very specific way using mathematical notation to explain why we believe our answer is correct. So let's start with just a basic review of piecewise functions, and you'll notice that these graphs are a reference to the previous set of notes for Lesson 1. As a reminder, in Lesson 1, we focused on finding function values. If you think back, we said that using this graph to find f of 2, I would look for the 2 on the x-axis and find the corresponding point of the graph, which is the place where y is equal to 4. For problem number 2, if I want to find where x is 2 on the x-axis and find the corresponding point on the graph, there are 2 points to choose from here. There's one with an open circle and one with a closed circle that are both have the x-coordinate of 2. However, the function value always refers to the point that has the closed circle. So that would, once again, be the value 4. And finally, for the last graph, when x is 2, if I map that up to the function, you'll notice again there's a closed circle here and an open circle here. The function value is always the point that has the closed circle, which again has a y value of 4. Now I'm reviewing this because although f of 2 is equal to 4 for all of the functions shown, each of the graphs looks very different. If we look at the graph around those points, this graph connects at the point that we were interested in. This graph is disconnected, and this graph seems like it wants to connect, but when it gets there, something weird happens and the closed circle is actually somewhere else. So what we're going to learn today is that we need a better way to describe the behavior of a function near a particular x value. And the way we do that mathematically is we use something called a limit. So let's go ahead and define a limit. A limit is a y value that a function approaches as x approaches a specific number. And this is the really important part. A limit tells us where the function intends to go. Now, up here we said function values are always focused on the closed circle. However, when we're looking at a limit, it's not focusing on the closed circle anymore because that piece of information doesn't give us a full picture. A limit tells us where the function intends to go. So we look at the behavior around a certain point. Sometimes around a closed circle, it looks like the graph is intending to go to that closed circle. Sometimes part of the graph goes to the closed circle, but the other side is headed towards a different spot, maybe an open circle like this one. And sometimes the graph seems to be heading towards an open circle from both directions, but the closed circle is just somewhere else. A limit is going to allow us to talk about the behavior around an x value, as opposed to just focusing on one specific point on the graph. Here's what limit notation looks like. So the word limit is shortened to lim. Limit of f of x as x approaches c is equal to L. In this notation, the x approaches c tells us the x value to get close to. And I'm going to use the word approach here because we kind of imagine sliding towards it and seeing what's happening as we slide in that direction. F of x tells us the function that we're using to evaluate this limit, and L tells us the y value the function approaches. So again, a limit is a y value that a function approaches as x approaches a specific number. Now, when we read this notation out loud, so when we're discussing it, when you hear me say these words out loud in a video, here's how I'm going to say them. I'm going to say the limit of f of x as x approaches c, whatever that number is equal to L, whatever that number is. Now, when we're learning in calculus, we're going to start with what are called one-sided limits. Now, here's what a one-sided limit says. We can slide towards a specific x value from the left side of the graph or from the right side. A left-sided limit is when we approach an x value from the left. This does not mean start at an x and slide to the left. It means start from the left and slide towards the x. So here's what that looks like. This says find the limit as x approaches 2, and you're going to see a little minus sign here. This little minus sign means from the left. So to evaluate this limit, I would find the place where x is equal to 2. Now on this graph, that would be right here. Imagine like this imaginary line. I'm going to slide towards that line from the left. So from the left of this line, slide towards it. And if I follow the graph from the left side towards the line, the blue line, I'm going to be following this portion of the graph towards this closed circle. So my limit value would be 4 because the y coordinate of this closed circle is 4. Now, in contrast, we can also have what's called a right-sided limit. A right-sided limit is when we approach our x value from the right. To denote that we're using a right-sided limit, in our limit notation, you'll notice we put a little plus sign here by the number. So in this problem, same exact graph, we're still going to approach the number 2, but we're going to do so from the right. So again, x is equal to 2 at this point on the graph, this kind of line. We're going to slide towards that line from the right, which means I'm following this upper part of the graph, because this part of the graph is to the left of the line and this part is to the right, which means I'm approaching this point right here. The y coordinate of that point is 5. Now, some students have trouble with this because they say, well, but wait, there's an open circle there. Remember, a limit is just telling us where the graph intends to go, not whether there's actually a closed circle there or not. So since I'm sliding towards this open circle, that's where I intend to go, which means my y-coordinate is 5. Now, after we've discussed one-sided limits, we can discuss two-sided limits. A two-sided limit is when we look at both one-sided limits. And this is really important. We have to look at both one-sided limits. If we ever just say the limit as x approaches a number, you'll notice that in this notation, there's no little plus and there's no little minus. If there's no little plus and no little minus, it means this is a two-sided limit. Now, the thing about two-sided limits is that sometimes they exist and sometimes they don't. A two-sided limit only exists if the limit as x approaches that number from the left is equal to the limit as x approaches that number from the right. Now, this is really an important calculus idea. A two-sided limit only exists if the left-sided limit is equal to the right side limit. So we will never say that a limit does not exist just because there's an open circle or a closed circle. The only time a limit does not exist is if you check two sides and they don't agree. Now, here are two possible scenarios. If I give you a graph like this and I say, please find the limit as x approaches 2. The limit as x approaches 2 is a two-sided limit. Because there's no little plus and there's no little minus. So I'm going to find the place on the graph where x is equal to 2. I'm going to slide towards that line from both sides. From both the left and the right, the graph appears to be approaching this open circle. Since the graph approaches the same value on both sides, we would say that the value of this limit is 3. Do not let the closed circle here confuse you. That might be the function value, but it is not the limit. It's not where the graph is approaching. It's just where the closed circle is. The second scenario would look something like this. In a similar situation, I might say find the limit as x approaches 2, which again is a two-sided limit, and I can tell that because there's no little plus and no little minus next to the number. So on this graph, I'm going to find the place where x is equal to 2 and slide towards it from both sides. What you'll notice is on this graph, there are two different points that I'm approaching. Because the value of the limit is not the same on both sides, we would say does not exist. And here is where we get to our learning target about justification. We would say because the limit as x approaches 2 from the left of f of x is not equal to the limit as x approaches 2 from the right of f of x. Now, when we justify our answer here, we don't need to write long sentences. We just need to say that the left side limit is not equal to the right side limit. But the notation here is important. You must have x approaching 2 from the left with a little minus, and you must have f of x here. You must have x approaching 2 from the plus, and you must have f of x here, and you must have a not equal to in the middle. With missing any of those components, you are not communicating your mathematical ideas correctly, and it will not be counted as a correct justification. Let's go ahead and just go through some limits so that we can practice this idea. I don't want you to overthink it. We're just looking at what happens when we slide towards a value from a particular direction. So for problem number 1, it says x approaches -4 from the left. Here's the place where x is -4. If I start from the left of there and I slide towards that point, the point that I'm approaching has a y coordinate of 0. If I slide towards -4 from the right, and again, this is from the right because there's a little plus sign. If I slide towards that point from the right side, I'm sliding towards the same point, which has an x or y coordinate of 0. Now, the third question here is really forcing us to think about both of these answers, because this says, what is the limit as x approaches -4? There's no left and there's no right, which means we need the two-sided limit here. So in order to figure that out, I'm going to compare these two answers. Since both answers agree and they're 0, the limit is 0. If those answers did not agree, I would say does not exist, and then I would explain why not as my answer. For problem number 4, it says, what is the limit as x approaches -2 from the left? So here's the place where x is -2. Now, there are two different points here, the closed circle and the open circle. If I'm sliding towards this from the left, the only part of the graph that goes left of there is this part. So if I slide from the left towards where x is -2, I'm approaching this closed circle, which has a y coordinate of 2. If I want the limit as x approaches -2 from the right, so here's the -2, the right side of the graph continues with this kind of semicircle here. So to slide towards that point from the right, I would slide towards this open circle, which has a y coordinate of 0. Now again, problem number 6 is really asking us to compare both of these answers. So this is a two-sided limit again. Since these two answers do not agree, they are not the same value, I would say does not exist. And to explain my answer, I would say because the limit as x approaches -2 from the left of f of x is not equal to the limit as x approaches -2 from the right of f of x. For problem number 7, we're asked to find the limit as x approaches 4 from the left. So if I go to this graph, here's where x is 4. From the left, which means this side, I'm going down in this direction. Now you might be wondering, well, what y value are you approaching? It seems like the graph keeps going forever. I would like to remind you that as you go down on a graph, the y values go towards -infinity. So because this part of the graph is going down like this, as I approach 4 from the left side, the y values are descending to -infinity. If I want to approach 4 from the right, I would go to the other side of this asymptote, and I would follow this part of the graph up. Again, I'd like to remind you that on a graph, if you go up forever, you're approaching positive infinity, so that would be a positive infinity as my limit. Now, if I want to find the two-sided limit, I'm going to again go back and check both of these answers, which do not agree. So I would say does not exist, and I would say because the limit as x approaches 4 from the left of f of x is not equal to the limit as x approaches 4 from the right of f of x. Last but not least, let's look at the last row of questions here. Problem number 10 says the limit as x approaches 1. Now we should notice right away here that this is a two-sided limit, but unlike in the previous questions where I asked you about a two-sided limit, I did not front load the two sides as the previous questions. So for this one, we're going to need to evaluate those two sides on our own. So the place where x is 1 would be right here, and I would be really careful about counting and paying attention to the spacing on the graph. If this is 2, then this is 1. So if I want to find that limit, I'm going to find the point on the graph, and I'm going to approach it from both sides. Both sides approach this same point right at the top of this semicircle, which has a y value of 1. Since the two sides agree, they can just be, the answer to the limit is just 1. Now, to kind of stretch you and sort of think about things in a little bit of a different way, if we ask when x approaches infinity. So as a reminder on a graph, x is the horizontal axis. So x goes towards infinity on this side of the graph. What this limit is asking us to do is just follow the graph that way. You can't approach infinity from two sides because infinity is if you just keep going forever. So if I keep going this way forever, it looks like this graph is getting lower and lower and lower and sort of flattening out. We call that a horizontal asymptote. So it appears to be approaching the x-axis, which I would say then has a y-coordinate of 0. So when x goes this way, the graph y values go towards 0. Finally, if I want to find the limit as x goes towards negative infinity, that just means that on the graph on the x-axis, negative infinity is this way. Since this graph just seems to keep going up and increasing, it's not getting flatter, it's just kind of going up, we would say that it's going up towards infinity, which is the y-coordinate for going up forever. So we would say infinity here. All right, thank you guys so much for watching and for kind of taking notes and learning on our introduction to limits, and I will see you soon.